So I'm Justin Sambur, I'm Assistant Professor of Chemistry at Colorado State University. So my group is interested in studying nanomaterials for different energy applications. So we're interested in energy production and storage, either producing electricity or chemical fuels. Nanomaterials have a lot of potential in this area, but one issue with nanomaterials is that each particle is different from the next. Each nanoparticle is different from one another, and they're not like molecules. And so we need to understand structure-function relationships and why certain nanoparticles are better than others. So my group uses microscopy tools to try to answer that question of, let's say, what is the best nanoparticle in a sample? And if we can understand that, then we can make more of those particles and hopefully make a better energy conversion system. The other major area of the group right now is we're studying smart window materials. So we're using nanoparticles as dynamic optical coatings, and these are things that are already on airplanes and rearview mirrors. So these are window coatings that switch color, and they prevent thermal radiation from entering a room, or basically prevent the room from heating up. And so these have huge energy saving potentials, these smart windows they're called. And we're watching single particles turning color in a smart window device. And we're learning how to maybe make windows that'll switch maybe 10 times faster than the current technology. I was able to work with HORIBA to build a custom microscope that would allow us to do single molecule imaging, photocurrent mapping, photoluminescence, microspectroscopy, Raman microspectroscopy, all on one setup, and it's so easy to switch between different modes of imaging. What I really love is how the instruments can really trigger off the LabSpec 6 software. So the LabSpec 6 software has ways to talk to different instruments, and we are totally leveraging that. It's just been awesome to use this microscope, and it's pretty easy for a new student to get trained on this instrument. And so it's been tremendous to get my research program up and running. As a postdoc, I had built an instrument like this, but we did not have the scanning capability. So we didn't have a nice, robust software package to talk to a stage to move the sample. I knew that this is easily done for commercial instruments. The problem is I didn't want the commercial geometry to excite my sample and detect. And so HORIBA was able to work with me. I wanted to have a certain excitation pathways and detection pathways on a certain microscope platform, and then have this robust software package to switch between all imaging modes. And that's what I have, and that's really been awesome. They were able to work with me to leave certain space on the table so I could add in my own optics. If you look at a picture of the table that day versus where it is today, we've added our own components, and they were able to let us do that. So other researchers have used a scanning photocurrent technique to map the energy conversion efficiency of a bulk crystal. We are applying that same method with better optics and a tighter laser focus to study these very ultra-thin, these 3-atom thick materials. We raster a laser across a sample, and when the light hits the sample, it generates electrons and charge carriers that we can separate and collect as electricity in our cell. These are the first spatially resolved photoelectrochemical measurements of these 3-atom thick materials. We have found what I call nonlinear scaling relations. So it means that we're getting more efficiency than you'd predict. When I couple these two materials together, they perform better than when they're isolated. So you put them together, you get more synergistic enhancement than you'd expect. We are actively exploring, what are the chemistry and physics that give rise to such a large enhancement effect. We also are looking at how the laser reflects back at the camera about the detector. And we're using this reflected laser signal to correlate structure and function, because it reports on, let's say, whether I'm on the edge of the material or on the interior of the material, different types of structural motifs. And through all this is what the field really wants to know, actually, is what are structure function correlations on the nanoscale? And so we're using our HORIBA microscope for that is the unique part of the group.